All right. So here's the plan for this week. It's Monday. So I say that like I'm surprised. Wednesday, we're gonna have a quiz on Wednesday. What's going to be on the quiz? Well, 4-2, 4-3, mins and maxes. All right. The sign test, concavity. There'll be a question that covers all of those things. So you can assume there's going to be some kind of a function. You're going to have to find local mins, local maxes. Tell me where it's increasing. Tell me where it's decreasing. Tell me where it's concave up, and tell me where it's concave down. Very generic problem. Don't expect it to be anything elaborate, have a lot of bells and whistles to it. It's just, it's our first quiz tried this way. So we'll see how it works out. So we're going to have a question on 4-2 and 4-3. Okay.
The quiz will be on the meeting, or it will.
Well, that's what I was going to ask you guys, how you wanted to handle this. I have no problem at all using class time for the quiz. If we want to do that, if we want to use the first 30 minutes of class, we can do that. That unfortunately eliminates 30 minutes of me answering questions and me having conversations with you about what's being done on the on the whiteboard. Or we can do the quiz at 7:45 to 8:15 after class. I know that's on your time, but that affords me more opportunities to answer questions during class. And before everybody starts chiming in, hang on a second, I've got to let Valeria's in the waiting room. Now Valeria's out of the waiting room. So before, what am I going to do? How am I going to decide when I give you the quiz? I'm not going to decide when I give you the quiz. I'm going to let you decide when I give you the quiz. So everybody just send me an email at school, sometime, not in the next 10 minutes, but by midnight tonight, tell me how you want the quiz administered. Do you want the quiz to start at 6 when class starts and end at 6:30, and then I join you at 6:30? Or you want to have class from 6 to 7:40 like we typically have class, and have the quiz go from 7:45 to 8:15. Remember, the quiz is going to be open book, open notes, open anything you want. Why is my wife?
But can you send it us before?
What I'll do, Rag, what I'll do is, hang on, I dropped my pen. But I wasn't flipping it for those of you that are keeping track.
I don't believe it.
Yeah, I don't want anybody going, oh my God, he's having
you. We got you. You dropped it. We got you.
Yeah, it was a dead drop. It was just hand out. That was all there was to it.
You said never.
The umpire called it a drop. So, what I'm going to offer you are two choices, Rag, just to make sure everybody's clear. When you send me an email, just let me know. Do you want the quiz during class time or after class? That's all I need to know from you, and I'll just take everybody's vote. And I'll send you a response first thing tomorrow morning and let you know what we're going to do.
But by email, all are here.
Yeah, just we're all on here, but I don't want to have to deal with it right now, Rag. I want to get going with class and get it all. I don't.
Yeah, but you can save the chat and.
I know what I understand exactly. I can sit here and count them, but I don't want to deal with it that way. I just want to do it outside class.
What we could do is do it after, after we do the class time, and then
that's one of the choices, Sam. I'm just saying, do you want to do it? You guys just send me an email. Let me know your vote. All right.
I think she meant voting after class.
Oh, yeah. I expect you to vote
after class.
I expect that. Don't do the voting now. Don't go send me an email right now. Right now, we're just going to have class.
I think Alyssa had a good idea. We can do it on the remind. Then it's all on one thing.
Okay, you can send it to my phone. That's fine too. I don't care how you get it to me. It's just everybody gets one vote. All right. We can't have Darren send in 46 reminds trying to sway them.
That's crap.
Because that's the kind of guy Darren is. So I've known him for years, so that's what you expect. So what are we going to talk about tonight? We're going to talk about. Hold on, just a sec.
What chapters is it on?
Okay, that's what I was gonna. I'm just gonna switch the camera over here, and we'll write it on the whiteboard so everybody's clear. All right. So here's where, that is on the whiteboard, right? Hey, look at that, it is. All right, so here's what we're gonna cover on the quiz, and I'll even write it out here so you can have it on the recorded version, and you can have it on the, you know, you can take a screenshot, you can do everything you wanna do with it. So the quiz is gonna cover sections, it's gonna cover sections 4.2 and 4.3. There's going to be one question. All right. And what do I expect that question to ask? I expect that question to ask you to, it's going to be just like the homework problems. You know, part A is going to be, where is F increasing and decreasing? Part B is going to be, find local mins and maxes. Part C is going to be, you know, where is F concave up and concave down? And then part D will be, find any inflection points. Okay, so that'll be one question on the quiz. And we'll start, when we come back from spring break, you know, the first Wednesday we're back, we have a test, but after that, we'll just start having a quiz once a week. And we'll, like I said, we can do the quizzes whenever you guys want to do the quizzes. I'm completely open to your direction. So that's going to be 4.2 and 4.3. Now remember, we didn't cover 4.4, and then we're going to do 4.5. We'll have a question, probably two questions, to be honest with you, on 4.5. That was L'Hopital's rule. And I can tell you right now, one of those questions is going to be just straight up L'Hopital's rule, meaning it's not going to be a problem where you have to worry about an indeterminate product or an indeterminate difference or an indeterminate power. It's going to start as a fraction. You're probably going to need to use L'Hopital's rule right off the bat. You're not going to have to do any extra work on it. You can just consider that to be the quote unquote easy one, or whatever you want to call it. But it's just directly going to be L'Hopital's rule. And then we'll have one of our indeterminate. That's not how you spell that. One of our indeterminates. I don't know if it's going to be an indeterminate product or an indeterminate quotient or an indeterminate difference, but it'll be one of those problems like we talked about last week, where you have to go through and make an adjustment to the problem prior to being able to use L'Hopital's rule, okay? So that'll be our quiz, and I will send it to you. What I'll do is I'll make a Google Drive link to my Google Drive, and I'll send you a PDF of the quiz, and then you can print it out at your house, do whatever you want, and then your job is to send me back a PDF version of that quiz. Okay, that's via email. Don't send it to me via Remind. I can't print anything via Remind. And I'll make sure you have all the directions on the quiz. The quiz itself will have all the directions written on how to return it to me, and get it to me in a PDF. And then we can, like I said, we can take the quiz. Come on, guys, I believe in you on this one. Okay, my wife's math, the elementary school class, has done this twice successfully already, so they can do this. You can do this. I'm sorry, I can't talk real loud because she's on the other side of the door teaching her class. But yeah, if they can pull this off, you got this. So we don't want to, we don't want to embarrass ourselves or anything. And so, if I was really, really, technologically savvy, I would just send you guys just, a Google survey question, have everybody vote, or a Survey Monkey question. But I'm not going to work that hard. I mean, I can do both of those things, but I'm just going to tell you right now, straight up, I'm just being lazy. So if everybody's got that written down, that's what our quiz is going to look like. So I'm going to go ahead and clean this off, and then go ahead and get started with class. Now, if you've been on the YouTube channel, I posted 2 new videos. We haven't covered them in class yet. I'm trying to put the videos on the YouTube channel ahead of time in case any of you are sufficiently bored and you want to be working ahead. So I posted a video today on 5.1, a full explanation, full lecture, and I posted a video on 5.2 called 5.2 Part 1. 5.2 is huge in two aspects. It's huge in the aspect that it's very long and there's a lot of material. Nobody said it was difficult. I didn't say it was difficult. Don't assume that big makes something difficult. There is a lot of material to cover, however, in section 5.2. So I posted a video today called 5.2 Part 1 because I'm an hour in and I'm halfway through 5.2. Again, no one's saying 5.2 is difficult. I'm saying there's a lot of material in section 5.2. So I will post the second half of that, the 5.2 Part 2. Probably I will get that recorded tomorrow. And then at that point, I will do a 5.2 homework solutions video as well. So there should be 2 more videos coming up, hopefully tomorrow on 5.2. If not tomorrow, they'll be posted on Wednesday. All right, so that's where we are on the videos. Hopefully you're watching those. I haven't been counting the views or anything like that. My ego can't handle it. And so we left off last week talking about our lecture was 4.7. We talked about L'Hopital's rule, which hopefully, other than it being an inordinate amount of calculator work, you didn't find to be overwhelmingly difficult. The good news is, on the midterm, you're going to have a L'Hopital's rule question. You'll be able to use a calculator. You'll have all the time you need at home, of course, to get it done. Well, you're not going to have 2 weeks to get the midterm done. I mean, I can give you a 2-week-long take-home midterm if you want, to go through a living nightmare of a midterm, but I have no intention of doing that. So my anticipation, just so everybody is a little more relaxed, perhaps, about the midterm, I do not have any anticipation, because you have open book, open notes, of augmenting or in any manner increasing the difficulty of my midterm in comparison to any other midterm I've ever given. You're going to get the same midterm in difficulty, or even maybe a step down in difficulty, not a step up, a step down in difficulty, because we do not get to share time together, even though you have open book and open notes, because fair isn't really the right word to use to describe our situation, because it's nobody's fault and there's no one to blame for this. It is what it is, and we're dealing with it the best we can. So when I would still study for the midterm, pardon me, as if it was a midterm. I would still prepare for the midterm. I've done plenty of take-home tests in my life, and you know me, I'm as lazy as they come. And I've gone into take-home tests where I, quote unquote, have not prepared. I've gone into midterms where I didn't prepare at all. And I've gone into midterms where I studied my you-know-what off. And it's a midterm. The more you study, the better you're going to do. Doesn't matter if it's take-home, doesn't matter if it's open book, doesn't matter if it's open notes, doesn't matter if I've made adaptations to the midterm to take into account your unfortunate situation. It's still a midterm. So the more you prepare, the better it's going to go. Jake wants in. Well, you know what? I'll let Jake in. All right. So hopefully Jake and Valeria are in now. Let me check the participants here. Yeah, they're with us. So that's nice. All right. So Jake, Valeria, for what you missed, the meeting's being recorded, of course, and so you can go.
Catch Jacob.
Hello?
Yep, Jake's here.
Okay.
You guys can go back and watch the first part of the meeting for when I post it tonight for anything that you've missed.
Okay.
Catch Jacob.
Okay.
So if anyone has any questions, if you would type them into the chat. Again, I'll do anything. If you have questions back on 4.5, I'll do those. If you have questions on 4.7, I'll certainly take care of those. I'm not particular about where the questions come from. assuming they're going to come from the book, and assuming, you know, they're not going to come from chapter 12 or something like that that we don't cover, then I have absolutely, I won't hesitate to answer any questions. So if anybody has any questions, just type them in the chat there. So far, nobody's typing anything. So that, because tonight's lesson is 4.8, which is a nice lesson. It's a section people generally don't hate. They don't find it overtly difficult. They don't find it overpoweringly complicated. Most people find it very approachable, and so, you know, it's a nice lesson to have this evening, because well, it's sunny here now, so hour ago I thought the world was ending, but now we're okay. I don't know, did anybody else get hail?
Yeah.
In the Northwest?
Yeah.
Yeah, we got some hail.
Yeah, we did.
It was pretty interesting. My son's home from Oklahoma. He came home Saturday, and he was like, oh, look, it's just like home. All right. So does anybody have, no one's typed a question yet, so we're good. If nobody has, okay, well, there's finally, we got Mario typed. Thank you, Mario. 4.7, number 25. All right. Let's take a look at 4.7, number 25. So 4.725 says, explain why Newton's method doesn't work for finding the root of the equation x cubed minus 3x plus 6 equals 0. So this is 4.7, number 25. And we have, well, we don't have an f of x, we have an equation. So we have x cubed minus 3x plus 6 equals 0. Now this clearly has roots. It's a polynomial, it's a cubic. We know from our pre-algebra days that this must have 3 roots. The choices, of course, are 3 real roots, or we could have 2 complex roots, our favorite kind of numbers, and 1 real root. Those are the only 2 outcomes. Remember, complex roots have to occur in pairs. So while this polynomial could have 2 complex roots, it's still going to have at least 1 real root. It may have 3. It's going to have 1 for sure. It can't have 2, because if it were to have 2 real roots, that would leave 1 complex root. We can't have that. Complex roots must occur in pairs, conjugate pairs. So what do we know from this? We know this crosses the x-axis someplace. It definitely has a root. But the question says, explain why Newton's method doesn't work for finding the root if the initial approximation chosen is x of 1 equals 1. So they told us our initial guess was 1. Okay. Now, what happens if our initial guess is 1? Well, Newton's method says if you want to go find x sub 2, that's going to be x of 1 minus, and then we know we're going to write this twice. And then we have that lame way to remember where the derivative goes that I gave you last time. And I told you to put the derivative on the bottom because the heavier one sinks to the bottom. So if we're going to employ Newton's method with x of 1 equals 1, our x sub 2 would be 1. X of 1 is 1 minus f of 1 divided by f prime of 1. Now what happens? Well, before we can proceed, we have to find, we haven't technically written down what f is. F of x is x cubed minus 3x plus 6. That's my function. And so f prime of x, right, we bring down the 3x squared. The derivative of negative 3x is negative 3. And so if I try to find f of 1, now I have 1 here, minus f of 1. What do I get when I put a 1 in here? I get 1 plus 6 is 7. Take away 3, that's going to give me a 4. Okay, so my numerator is going to be 4. And when I put 1 in here, I get 3 times 1, that's 3, take away 3, and I get 0. And that leads me to 1 minus undefined. Now, that clearly is not a 0. It's not a root. It's not a solution. It's a mistake. And when I say it's a mistake, it's not a mistake in the context that we've done something erroneous in our calculation. It's a mistake, in fact, that we know we have roots. We have either 3 of them or we have 1 of them. So there is a root. A root exists. There's a root out there to this polynomial. But Newton's method failed right here, right? It failed. And so the question that's being asked to us in number 25 is, why did it fail? And it failed because we made a heinous first guess, right? We picked, out of every number on the number line, we picked one of the 2 possible numbers that would have caused the derivative to be 0. So what has happened for us here is not an example of Newton's method not working. We can use Newton's method to find this root.
Excuse me.
Yes.
Mario got kicked out of the room and he's in the waiting room.
Oh, Mario. All right, Mario's back. It was better without him. Sorry, Mario. I don't know why he got kicked out.
Like right when I sent it, I got like my internet went out or something. So I was like,
Oh, okay.
Kevin just kicked you out.
Yeah, I did. I did. It's all me. It's all me. And by the way, thank you, because the Surface Pro's all the way across the pool table, so I appreciate you guys letting me know. So what was wrong with this approach? It wasn't a problem with Newton's method in the context of Newton's method doesn't work. It was a problem with Newton's method in the context of Newton's method says, don't pick somebody that causes the denominator to equal 0. So what we do to fix this, right, is use a different x of 1, right? If we would pick anything, practically anything on the number line, other than 1, 1 causes this to be 0, as does -1. So if we would have picked anyone as our initial guess, other than 1 or -1, Newton's method would have worked beautifully for us. It would have found us our 0 that we were looking for. But unfortunately, we just had the misfortune of picking an initial guess that caused the derivative to equal 0. So we want to avoid that at all costs. So if I give you a problem on the midterm and I don't give you an initial guess, make sure when you make your initial guess, you don't pick the number or the 2 numbers or the 3 numbers, whatever it turns out to be, that causes the derivative to be 0. And if that happens, go make yourself another guess. Okay, so that's number 25. And now 4.3, number 11. All right, so you're going to have to give me a second, guys, so I have to turn some pages here. 4.3, number 11. Oh, Trey, you're lucky I like you. All right, so I'm going to go ahead and clear this off. So, like I said, it'll be on the recorded version of class, of course. This is where I normally ask you guys during class, so where are you guys going during spring break? But I don't have to ask you that now. So some of you are going to go to the laundry room, some of you are going to go to the bathroom. It's going to be an exciting spring break.
Do we still have a spring break?
You guys are still off, quote unquote, next week from me. I don't know what that means. I mean, I may hold a couple of office hours, voluntarily only, of course.
Okay.
Yeah, I don't have a problem doing that at all. So 4.3 is very similar to the question that I had just diagrammed right here that I said would be, the first question on our quiz. 4.3, number 11, gives us a function. It says f of x equals, and we get sine x plus cosine x on the interval from 0 to 2 pi. inclusive of 0 and 2 pi. So they want us to describe for them the intervals on which this function is increasing and decreasing, where, if anywhere, this function has a local min and a local max, and what those are, the intervals where this is concave up and concave down, and any associated inflection points. All right. So this is one of those problems where, as long as we follow the format and keep our organization straightforward, this problem, albeit long in steps, is not overpowering in terms of complexity. All right. So I like, because I know that I'm going to need the derivative for increasing and decreasing. I'm going to need the second derivative for concavity. I like to begin by just finding the derivatives right off the bat. The derivative of sine, of course, is cosine. The derivative of cosine is negative sine. I don't need the chain rule or anything because there's no 2 inside here and it's not x squared. Now I know I'm going to need the second derivative, so I'm going to go ahead and find that. The derivative of cosine is going to be negative sine. The derivative of sine is going to be cosine, so that's going to be minus cosine x. Okay, so I found my first derivative and I found my second derivative. And now I'm going to set out to start answering their questions. Part A says, where is f increasing and decreasing? Okay, where is it increasing and where is it decreasing? Now, how are we going to answer that? We're going to answer that by taking our derivative, setting it equal to 0, that's one side, and we're going to take our derivative and we're going to check to see if it ever fails to exist. That's the other side. So to do this problem, we need to do both of these every single time, because this is going to give us what we call our critical numbers, and our critical numbers then transfer onto our sign test so we can conduct the sign test. But first, we have to find the critical numbers. So we're going to do this to find the critical numbers. So I take my derivative and I get cosine x minus sine x, that's my derivative, equals 0, which means we're looking for cosine x. I'm going to move the sine to the other side. We want to know, when does cosine equal sine? When does cosine equal sine? Now, there's two ways to do this. One of them is to draw the graphs and try to determine where they intersect. Maybe if we draw graphs especially well, then we might be able to do that. The other way to do it is just to think it through based on our knowledge of trigonometry. Cosine and sine equal each other where? That's the question we're being asked. So if we draw our what do you call this, Gav? Oh yeah, the coordinate plane. I'm sorry, I couldn't think of the words. So we have all students take calculus. Now, what do we know? We know that they being sine and cosine, they have to equal each other. So they both have to be positive or they both have to be negative. The only place they're both positive is here. If we were in quadrant 2, this side would be negative, but this side would be positive. That can't be equal. If we were in quadrant 4, this side would be positive, this side would be negative. That can't be equal. However, in quadrant 3, they're both negative. So those are our two options. So our quadrants, right, because whenever we're asking ourselves trigonometry questions, we always ask ourselves what quadrant and what's our reference angle. Those are our two questions we ask every single time. Our quadrants here are quadrant 1 and quadrant 3, because in quadrant 1, they're both positive. In quadrant 3, they're both negative, so they can equal each other. Okay. Now, when does sine and cosine equal each other? We know, hopefully, that this is going to be a 45-degree reference angle. Now, how did I come to that conclusion? Well, in my mind, I pictured a 30, 60, 90 triangle. And I thought about this angle, and I said, well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Those don't match. I thought of this angle, and I said sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and I said those don't match. So I eliminated the 30, 60, 90 triangle. Then I thought about the 45, 45, 90 triangle. And I thought, well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and those do match. So my reference angle is going to be pi over 4. Okay, pi over 4. Now remember, our solutions are which angles work. So where are we going to go from here? Well, we have a reference angle of pi over 4 in the first quadrant. And we have a reference angle of pi over 4 in the third quadrant. So we need to write those two angles down. So in the first quadrant, that's going to give us theta equals pi over 4. In the third quadrant, I'm sorry, it's supposed to be an x, isn't it? I'll fix that. In the third quadrant, this angle is pi. Now, I like to write pi however I need to write pi. So I'm going to write pi as 4 pi over 4. So I have to go 1 pi over 4 past 4 pi over 4. So I get 5 pi over 4. Those are my critical numbers that I determined from setting my derivative equal to 0. Now, what about failing to exist? Well, when we go back and we look at our first derivative, we have cosine minus sine. Those are continuous functions, i.e., they're defined everywhere. They never fail to exist. So there is no solutions here. We can write NA for this. So where are we now? Well, we're up to the sine test. That's where we are, right? We're up to our sine test. And we know how to conduct the sine test. We draw the number line. We write our critical numbers down. We have pi over 4, and we have 5 pi over 4. Right? Now remember, this stops at 2 pi. This stops at 0. Right? Now, there's something about this problem that's a little trickier than some of the problems we've talked about in the past. We always factor the derivative and write the factors right here. We can't factor that. Cosine minus sine does not factor. So the best we can do, right? The best we can do here is just to write the derivative right here. We can't factor it. It doesn't factor. Those are terms. We can't write a term here and a term down here. We don't write the terms. We write the factors. So where do we go from here? We pick test points in each of these intervals. Right? That's what we're going to do. We need an angle, right, between 0 and pi over 4. So I'm going to use pi over 6. I'm going to pick pi over 6 because that's between 0 and pi over 4. I need a number between pi over 4 and 5 pi over 4. I'm going to pick pi. Right? Somebody nice, somebody easy. I need a number between 5 pi over 4 and 2 pi. So I'm going to pick 3 pi over 2. Now you could pick 11 pi over 6. You could pick anything you want. I'm just trying to make this as simple on myself as possible. Okay? Now, from here, we go ahead and insert each of these numbers into our derivative. So we're going to put pi over 6 in here. Pi over 6 is here, right? This is pi over 6 right here. Pi over 6 is 30 degrees. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6, right? Sine of pi over 6 is 1/2. Root 3 over 2 minus 1/2. Root 3 over 2 is bigger than 1/2. So root 3 over 2 minus 1/2 turns out to be a positive. So I'm going to put a plus right there. Right? Now, where do I go from here? Well, I'm going to put pi into here. Right? Now, I don't necessarily remember cosine of pi, sine of pi. So what I like to do when I'm stuck on something like this, I draw myself a quick sketch. I'll draw sine here. I'll draw cosine here. And I know this is pi and this is pi, and that's going to help me out. Cosine of pi is going to be -1. Sine of pi is going to be 0. -1 minus 0. That's going to be negative. Now I got to put this number in there. Well, 3 pi over 2 is on my graph. Cosine of 3 pi over 2, cosine of 3 pi over 2 is here. That's 0. Sine of 3 pi over 2 is -1. 0 minus -1. 2 minuses make a plus. So we right now have been able to determine that our function f, based on this sign test, f is increasing on. And now remember, you're only allowed to say you're increasing when your derivative is positive. So you want to be very, very careful here. 0 is one of our numbers. What is cosine of 0? Cosine of 0 is 1. What is sine of 0? Sine of 0 is 0. 1 minus 0. That's a positive number. So we have to make this close. Now that's the kind of thing that on a midterm, we just blow right by. We just blow right by it. We don't even think about testing the endpoint to see if it's positive or negative, and therefore we just make this an open interval, or maybe we just slap closed interval symbols down. We don't analyze.
Kevin,
Go ahead. Go ahead.
can you explain that part a little bit better for me? The
One more
closed
time.
parentheses or the.
Yes, yes. Let's go through that from the top. They have told us that we begin at 0. 0 is our first number. Now, we can see, I'm just going to take this off. We can see that we have a plus for our derivative between 0 and pi over 4. So we're going to write increasing from 0 to pi over 4. Now let's just leave the brackets off. And we can see from our sign test, pardon me, that we're positive from 5 pi over 4 all the way to 2 pi, right? So is everybody okay that this ends up being one interval and this ends up being the second interval based on my sign test? Now, where things can get a bit, go ahead, Adam. Oh,
I just said yes. I'm with you so far.
That's fine. Now, where things can get a bit tricky is typically when you do a sign test, the only numbers on here are critical numbers. But because this problem was a gift, and they told us only to work between 0 and 2 pi, and that is a gift, because if they didn't tell us to work between 0 and 2 pi, we would have to find all the numerical multiples of pi over 4 and all the numerical multiples of 5 pi over 4 and use all. It would not be fun. Okay, that problem, I'm not going to give you that problem. Don't worry about that problem. It won't be on the midterm. It won't be on the final. It won't be on any quiz I ever give you. So we are able to say, beyond a shadow of a doubt, we know what happens right here. Right here, the derivative equals 0. So that cannot be increasing, because increasing means f prime is greater than 0. Greater than, strictly greater than. So at pi over 4, our derivative is not greater than 0. Our derivative equals 0. It's a critical number. We found it by setting the derivative equal to 0. Likewise, 5 pi over 4, not greater than 0. 5 pi over 4 equals 0. So those are open.
Okay.
What happens at 0? Well, if we plug 0 into this equation, this is our derivative. If we plug 0 in here, cosine of 0 is 1, right? Cosine of 0 is 1. Here it is on the graph.
Right.
Sine of 0 is 0. 1 minus 0. Yes, it's greater than 0. It turns out to be 1. So it works. So we would say, even though it's a point, we would say our function is increasing at that value because its derivative is greater than 0. Now, what happens at 2 pi? Well, at 2 pi, cosine is 1 again. Sine 0 again. 1 minus 0. 1 minus 0 is 1, greater than 0. So we would be forced, if we wanted to write our answer correctly, to include those two closed brackets in our solution. All right? And again, that only comes up typically when you have a predetermined interval that you've been asked to work upon, so that there is a left-hand endpoint and a right-hand endpoint to your analysis. Now, the other part of the question is, where is f decreasing? Well, f is decreasing between here and here because we have a minus. So where is it decreasing? It's decreasing between pi over 4 and 5 pi over 4, right? That's where f is decreasing. Now, it's going to be open on both ends because we know that's 0. The derivative is 0 there, not greater than 0, 0. So that's not increasing or decreasing. And it's 0 here, so that's not increasing or decreasing. So that's the answer to part A. Now, before anybody panics and thinks to themselves, oh my goodness, all that work just to get part A, we're done with part B. Part B is finished as well. Part B is on the whiteboard right now. When we get these problems, it says, part A always says, where is this increasing? Where is this decreasing? Part B always says, find me local mins and local maxes. Well, okay. By doing what we've done, we've already answered that question. Because if we take a look at our graph is right here. This purple thing is our graph. Now, I get it. It's not the graph in the context that you and I normally speak of the graph. But this is the graph in the context that we need, because it tells us between here and here, we're increasing. Our graph is going up. And we don't know what the graph of this looks like. I don't know. You don't know. We haven't drawn it. But between 0 and pi over 4, it's going up. Between pi over 4 and 5 pi over 4, it's going down. And between 5 pi over 4 and 2 pi, it's going back up. What does that mean to us? Well, that means right here, my graph is going up, and then it starts going down. So this point right here is going to be a local max, because the graph is going up, and now the graph is going down. But here, at this number, the graph is going down, negative, the graph is decreasing, and then the graph is increasing. This is going to be a local min. I don't know why I wrote max. I'll just do this, and it'll look like it's in it. So we know where the local max is, and we know where the local min is. The local max is at pi over 4. So how would we answer part B? We would answer it correctly, okay? Correctly. Now, I'm not being facetious there. What do I mean by we would answer it correctly? I mean, we would read the question and make sure we give them the answer they asked for. Part B clearly asks, find the local maximum and minimum values. It does not say, where did they happen? It says, what are they? So we know our local max is whatever f of pi over 4 is. Now, we don't know what that is. We're going to have to figure that out. We're going to have to do the arithmetic to find that. That's our local max. Where it happens is pi over 4. So we have to be careful on the quiz or on the midterm or on the final that we answer the question Kevin gives us. If Kevin says, what is the local max? He doesn't want to hear pi over 4. That's where the local max is. He wants to know what it is. So we have to go find f of pi over 4. Now, that's not hard. We can all do that arithmetic. F of pi over 4, f of pi over 4 is going to be sine of pi over 4 which is root 2 over 2, plus cosine of pi over 4, which is root 2 over 2, and we get 2 root 2 over 2's, or we get the square root of 2. So our local max is root 2. Now, if somebody said, where does it happen? We're writing pi over 4. We got to make sure we answer the question correctly. No matter what I ask, and I don't have to be tricky on this part B question on the quiz, midterm, or final. No matter what I ask, half the people taking the test give me the other number. It always works that. It's worked that way for 20 years. I'll ask you, where does it happen? And somebody's going to tell me root 2. And I'm going to look at this and I'm going to go, no, I don't think it happens at root 2. Or I'm going to say, what is the maximum? And you're going to tell me pi over 4. And I'm going to go, I don't think pi over 4 is the maximum. So you need to, when you're studying this, you need to tell yourself, I'm going to answer the question I'm asked. That's what I'm going to do here. Now, they also want to know what is our local minimum? Our local min is f of 5 pi over 4. And we can find that. We know what that is. F of 5 pi over 4 is going to be, we're going to put 5 pi over 4 in here. Now, remember, 5 pi over 4 is in the third quadrant. It has a reference angle of pi over 4. It's this triangle right here. So sine of this angle is going to be 1 over root 2, but we're in quadrant 3. So that's going to be minus root 2 over 2. Cosine, again, adjacent over hypotenuse, root 2 over 2, quadrant 3, negative, minus root 2 over 2. And we get negative 2 root 2 all over 2, or negative root 2. So these would be the answers to the question they proposed to us. All right? We want to make sure that we answer the question we're given. So this is what I meant when I said we don't have to do any more work for part B. Part B is here. It's right here. It's on the picture. We just have to interpret the I'm going up, I'm going down, I'm going down, I'm going up, and we can find our local mins and local max. All right. So that's A, that's B. And now I'll do part C, and then we'll all go to bed because it's going to be 10:30. I'm just kidding. It's not that late. There's still 21 of you participating in class. So let's get this on. Kills me every time I erase this stuff. It's like, oh, all that work. Shut the hell. Sorry, gone. Not shut there. Just gone. All right. So let's dry this off. And now we'll proceed with part C. Now, what does part C ask? Part C says, hey, can you tell me when we're concave up and concave down? And the answer is yes, I can, because I just did exactly the steps that I'm going to need in part A. And if I repeat those steps in part C using the second derivative instead of the first derivative, I'm going to get my answers. That's the key to concavity. So we begin, right? We begin the whole conversation about concave up versus concave down. And it's going to look very similar. F double prime equals 0. F double prime fails to exist. So it looks exactly like what we did before. The only difference being we've switched to the second derivative. So we begin. We take the second derivative. And what does it get? That gets us negative sine x equals positive cosine x. So this is going to be very similar to the question that we just asked ourselves. Except this time, instead of wanting them to have the same sign, we want them to have the opposite signs. Now we know which quadrants they have the opposite signs in. We know one angle is now going to be in quadrant 2 because here sine is positive, but cosine is negative. The other answer is going to be in quadrant 4 because cosine is positive and sine is negative. Now, if you're looking up here and you're going, wait, quadrant 2 doesn't work. We want sine to be positive. No, we don't. We just need them to be opposites of each other, right? It doesn't matter where the negative goes. We can multiply both sides by -1 and it pops on the other side. Now, we've already done this analysis, right? We know our quadrants. Our quadrants are going to be 2 and 4. And we have already done the work. We know what our reference angle is going to be. It's going to be pi over 4. And we did that work on the last problem. Now, it's not always the case that whatever your reference angle was on part A turns out to be your reference angle on part C. But we've got a gift here, so we're not going to look a gift horse in the mouth because, you know, next thing you know, you find a horse 22 years old. So you learn this kind of stuff in Greenfield. So what do we get for our answers here? We get this angle, right, which is going to be x equals 3 pi over 4. And x equals, down here, we get 7 pi over 4. Once again, sine, cosine, continuous, never fail to exist. So this ends up in NA. So now what do? We perform our sign test. We do exactly what we did before, except instead of using the first derivative, we're going to use the second derivative. So we do our sign test. So we go across here. Now remember, it starts at 0, it ends at 2 pi. Our first critical number is 3 pi over 4. Our last critical number is 7 pi over 4. And once again, we're faced with a second derivative that does not factor. Okay? It doesn't factor. We have negative sine minus cosine. Right? It doesn't factor. We can't pull anything out. I mean, okay, we can take out a -1, but what good is that? We might as well just leave it in there. So we need a number between 0, 0, and 3 pi over 4. So I'm going to use pi over 2 as my test point there. I need a number between 3 pi over 4 and 7 pi over 4, so I'm going to use pi. Again, trying to keep it as simple as possible. Now I need a number between 3 pi over 4 and 2 pi. So I'm going to use 11 pi over 6. Right? That one took a little thinking. So those are going to be my test points. I'm going to draw my graph of sine and cosine again. All right, I'll draw those again. Here's sine. Here's cosine. I do this every time so I don't screw it up. Now I've got to put pi over 2 into here. This is sine. Sine of pi over 2. Pi over 2 is right here. Sine of pi over 2 is 1, but I have a minus, so that's -1. Cosine of pi over 2. Cosine of pi over 2 is right there. That's 0. So I have -1 minus 0. That's going to be negative. I'm going to plug in pi. I have sine of pi. Sine of pi is right here. That's 0. I have cosine of pi. Cosine of pi is right here. That's -1, but I have a negative. So that negative times my negative makes this a plus. Now, these do not alternate on every single problem. Please do not get the idea that because that's minus, we could just write the rest down. Nope, got to check them every time. Now we need 11 pi over 6. Now, I don't know where 11 pi over 6 is on this picture. So I'm going to have to draw my 30, 60, 90 triangle. And I've got to remember that 11 pi over 6 has a reference angle of pi over 6, and I'm in quadrant 4. Quadrant 4. So now what do I need? I need the sine of this. Well, the sine of this is opposite over hypotenuse. That's going to be 1 over root 2. I'm just going to write it down. But we have a minus in front. But in the fourth quadrant, sine is already minus. So now we got to keep track of all these minuses, right? The reference angle gives me 1 over root 2, opposite over hypotenuse. But I'm in quadrant 4, and I'm doing sine, so I get a negative. But my function has a negative, so now I get a positive. Okay, I don't want to screw this up. We're too smart to miss this kind of stuff. Now, what do we have to do? We got to go minus. I need cosine of this. Cosine of this is √3/2. I'm in the fourth quadrant, so that's positive. So that's just going to be √3/2. Well, that's going to be a negative number because this is bigger than this and this is negative. So this is going to be negative here. So we now know where we're concave down and where we're concave up, almost. Because once again, we have these dreaded endpoints. We thought they were a gift because they allowed us to stop having to do sine and cosine forever. And they are a gift because checking the endpoints is a lot easier than trying to write 2k pi after all these answers. So what do we conclude? We conclude F is concave up on. Now, where is it concave up? It's concave up from 3π/4 to 7π/4. And we know beyond a shadow of a doubt, those are open because those are critical numbers and the derivative, pardon me, the second derivative equals 0 there. So we know that those are not places where the second derivative is positive. Those, because that's what concave up means. Concave up very specifically means the second derivative greater than 0. But for us, our second derivative equals 0 there. It equals 0, okay? So where is F concave down? Well, here we're going to face the same analysis that we faced in the last example. We have concave down between 0 and 3π/4. And between 7π/4 and 2π. Again, we know that's not closed. That's not greater, sorry, concave down, of course, doesn't mean greater than 0. Concave down means f double prime of x is less than 0. We know that's not less than 0. It equals 0. We found it to equal 0 there. So we know those are open. What goes on at 2π? Well, we got to find out. We go back to our drawing. We look at sine of 2π, 0. We look at cosine of 2π, 1. So what does this turn into? It turns into sine, which would be 0, minus cosine, which is 1. 0 minus 1 is negative. Negative. That satisfies f double prime of x less than 0 because it turns out to be -1. So we have to put a closed bracket on that 2π. 2π works. My second derivative is negative. By exactly the same argument, because of the symmetry of sine and cosine, we're going to get a closed bracket here. So that's our concavity, concave up, concave down. The last part of the question, and it always mystifies me how this never turns out to be part D. It always turns out to be inside of part C. I don't know what the inflection points did back in the day to somebody, but they pissed somebody off because they don't get their own part. So mins and maxes get their own part. Inflection points never get their own part. So it also says in part C, and find the intervals of concavity and the inflection points. Points. They want the inflection points. What is an inflection point? An inflection point is where concavity changes. We don't care how it changes, it just has to change. So we have inflection points at. And now they want points. They specifically ask for inflection points. So we're going to have to provide them with the inflection points. So one of them is going to be 3π/4, and then whatever the y value is that goes along with that. And the other one is going to be 7π/4, and whatever the y value is that goes along with that. So we're going to have to find the points. We want to make sure we always answer the questions they ask us to. Otherwise, it gets really frustrating when we're grading the test and we asked a very clear question and you answered a different question. You haven't done anything wrong, but you never addressed the question you were asked. So where do we go from here? what do we do next? Well, we got to plug these in, right? We got to plug 3 pi over 4. Now, we have to know the inflection points. These are the inflection points of f. So we got to make sure we plug it into here. The last thing you want to do on the test is plug it into the second derivative. That'd be silly. You're looking for the inflection points of f. F is concave up. F is concave down. F has inflection points. So we've got to plug 3 pi over 4 into sine. Okay, 3 pi over 4 is right here. Sine of 3 pi over 4 is going to be positive root 2 over 2. Because it's in the second quadrant, sine is positive. Cosine, we got to plug in cosine of 3 pi over 4. Well, cosine of 3 pi over 4 is going to be negative root 2 over 2. And we're going to get 0 here. When we do 7 pi over 4, cosine is going to be the plus 1 now. It's going to be root 2 over 2. But sine in the fourth quadrant, sine is going to be negative. So it's going to be minus root 2 over 2. And we're going to get 0 here. And that's the answer to our question. It's been nice seeing you guys. The semester's over and we're out. Everybody just check your Blackboard for tomorrow for your semester grade. It seems like that problem took pretty much the whole semester. So, and Kylie, that's not a knock against you. Please do not anticipate or interpret that way. It's a great question. I'm glad you asked it. And it allows me to once again go through all these steps. And once again to put on video all the steps. So assuming that somebody was smart enough to push the record button. Oh yeah, good, it's recording. All right, so where are we gonna go from here? Well, my grandmother would say, to hell if you don't change your ways, but you know, that's my grandmother. She's dead and in hell. So it's okay, don't worry. Don't worry about it. I don't even mind saying it on video. It's just a fact. It's okay. She was a good grandmother. She just wasn't the greatest person in the world. She was a good grandmother. So if you get to go to heaven for being a good grandma, my grandma's in heaven. You have to be a good person. Yeah. So anyway, enough about my family. Oh, it's still no puppy. That's Thursday. Sorry. We're getting closer, though. We're getting closer. We've got a list of names. I'm not going to ask your opinion because I don't care about your opinion. All right. So we're going to pick up 4.8. Right? We're going to finish chapter 4 tonight. That's very exciting. I mean, it should be very exciting because that leaves us 5 sections of chapter 5. And believe it or not, this nightmare called Calc 1 comes to a close. All right. And based on whoa, what happened to the whiteboard? Has that blue line always been way up there on the whiteboard, or did I move it when I was erasing? Sorry, here's my back. Making it better. Oh, man. Sorry. I'm just, my OCD-ness is kicking in here. All right. So we're going to talk about 4.8. And 4.8 brings to a close our chapter 4, which is applications of derivatives. And then what does that mean? That means, here, I'll sit back down here for a second, put myself back on here. Hey, look at there, I'm still here. And I have not gotten better looking. So we will have, we'll have completed chapter 4, which is huge because that leaves us 5 sections. Hey, look, we can see my wife's back. Oh, she's over there. That leaves us 5 sections in chapter 5, and we're done. We're finished. This nightmare that I said of Calc 1 comes to a close. So we're going to talk about 4.8 tonight. Now, here's the great news about 4.8. It really belongs in chapter 5. I don't understand Mr. Stewart's approach. I never have understood Mr. Stewart's approach. Mr. Stewart puts this in chapter 4. I have no idea why. I truly don't. What we're doing tonight is the beginning of our conversations about the integral, the last topic we have to talk about. There's really only 2 things you learn in Calc 1. Derivatives, integrals. That's it. That's what you learn. Now, I know we've done a lot more than derivatives, but in essence, all we've talked about since we began this way back when it was still dark outside when class started and dark outside when class ended was, and more importantly, I guess, back when we could leave the house. Sorry, I forgot about that part. all we've talked about since then is the derivative. We began talking about the derivative. That's where we began our first night. What is the derivative? Why do I care about the derivative other than because Kevin says I have to care about the derivative? So where do we go now? Now we go in a different direction. We go in the direction of the integral. What we're going to discover before we close the door on our class is we haven't really made very long of a journey. Integrals and derivatives are highly related, okay? Highly related. And that relationship is going to become evident tonight, to be honest with you. It's going to become evident tonight. So we're going to talk about section 4.8. And as I said at the beginning of this little session, nobody hates this section. Rarely do you have students who say, I despise section 4.8. I don't like this section. It's not bad. It's maybe that's why he put it in chapter 4, because he thought, I'll give him something nice at the end. Maybe that was his thinking. So I'll switch us back over to the whiteboard, and then I'll do our lesson on section 4.8, and I'll check back in with you here, and then we'll call it a night and not have to drive home. At least we're all saving gas money. We got that going for us, right? Our cars are going to last a lot longer. I mean, I just got new tires before the lockdown started. I'm thousands of miles ahead already on my tires. So Clarue is going to go out of business waiting for me to come back and buy new tires, because they've only been in business since like 1910 or something. So it's me that's going to put them out of business. All right. So not that I'm making this as an advertisement for Clarue tires, but I don't know why as a resident of Bakersfield you'd go any place else to buy tires, but you guys all got your favorite places. My dad owns, well, okay, that makes sense. All right, so here we go. I'll get this off me because me, I just talk and talk. And now
You need to start getting sponsorship.
yeah, I'll call George tomorrow and tell him that I put a shout out on my YouTube class for him and see if he'll give me a deal on my new set of tires whenever that. All right. So 4.8 is the antiderivative. That's what it's called. 4.8 antiderivatives. Now, what does that mean? It literally means exactly what it says. Instead of taking the derivative, we're going to undo the derivative tonight. That's what we're going to do. We're going to ask ourselves the question backwards. We're going to start with the answer to the derivative problem and say to ourselves, gee whiz, golly gee willikers, Batman, I wonder who we took the derivative of to get this answer. Now, while that sounds kind of heinous and kind of complex, it turns out to be relatively simple. It turns out that we know derivatives a lot better than we think we did. For example, I think everybody in the room knows who I take the derivative of to get e to the x, because that's the kind of question we're going to ask ourselves tonight. We're going to ask ourselves, who do I take the derivative of to get e to the x? We're going to ask ourselves, who do I take the derivative of to get cosine? That's the question we're going to ask ourselves. Who do I take the derivative of to get secant x tangent x? This is the question that we're asking ourselves in section 4.8. That's what an antiderivative is. An antiderivative is the function that goes here. We're starting with the answer to the derivative and working backwards. And we all know who you take the derivative of to get e to the x. You take the derivative of e to the x to get e to the x. We all know who you take the derivative of to get cosine. You take the derivative of sine to get cosine. And we all know who you take the derivative of to get secant tangent. You take the derivative of secant to get secant tangent. And if you're thinking to yourself, well, gee, Kev, you asked 3 simple questions. That's because the hard questions we can't answer. The joy about integration, okay? And there is great joy coming your way when I teach you the integral. The joy about integration is that integration is an art form. It is beautiful, it is elegant, and it is filled with a sense of satisfaction that the derivative does not possess. Anybody can take a derivative, all right? A derivative is like mashing potatoes with a sledgehammer. You're going to get your potatoes mashed, but there is nothing pretty about that process at all. Integration is elegant. Integration is the 5-course meal presented in a beautiful setting where the presentation is as important as the flavor. That's integration compared to differentiation. Anybody can differentiate. I understand that you're just learning how at this point, but anyone can take the derivative. I can write a function down. You can write a function down, and we can find its derivative. Integration doesn't work that way. The reason I picked these 3 functions is because we can answer the question for those 3 functions. But if I write something else down that seems arbitrarily simple, it seems equally as easy. If I ask you something like this, gee, who do you take the derivative of to get tangent? You can't answer that question. That question is not answerable by any knowledge you have at this point in time. We don't know whose derivative gives us tangent. Right? We don't know the answer to that. Because if I take the derivative of sine, I get cosine. If I take the derivative of cosine, I get negative sine. If I take the derivative of tangent, that's not what we're doing here. But if I do take the derivative of tangent, I get secant squared. If I take the derivative of cosecant, I get negative cosecant, negative cotangent. If I take the derivative of cotangent, I get negative cosecant squared. If I take the derivative, who did I forget? No, I got them all. Nobody's derivative turns out to be tangent. So the answer to questions like this, while seeming to be relatively simple, turn out to be a little more complex, a little more thought-provoking, a little more, I would say, interesting. Integration is the direct opposite of differentiation. Antiderivatives are elegant. Antiderivatives are beautiful. Antiderivatives involve thinking. Now, if it sounds like, I'm infatuated with antiderivatives, the truth of the matter is I am deeply and heavily infatuated with antiderivatives because antiderivatives lead you to a field called differential equations, which is equations with derivatives in them, and you'd like the derivatives to go away. So you anti-differentiate to get rid of them. And yes, that's the next step with equations, not the step you and I are going to share, not even the step you and your Calc 2 teacher are going to share. After calculus, your next interaction after calculus with derivatives is we put them in equations. That's what engineers do. We solve equations. I'm not an engineer. I spit up in my throat a little bit when I said we. But that's what engineers do. They solve equations with derivatives in them. We call them differential equations. And how do we do that? We anti-differentiate. That's what we do. Well, why then, if I'm not an engineer, am I so infatuated with this world? I'm infatuated with this world because my master's degree is in the study of differential equations. That's what I studied in graduate school. And this is the beginning of that journey for me. So that's why I'm kind of, waxing poetic or attempting to wax poetic about antiderivatives. So what are we going to do tonight? Well, we're going to just ask ourselves a couple of questions and then we're going to be done, to be honest with you, because we are not going to get any kind of powerful steps to find antiderivatives this evening because those steps are in chapter 5. Tonight, we're just going to get the flavor of the meal. We're definitely not going to get to taste it. We may be able to smell it. We may get a sense, but that's all the more we're going to get. So we're going to start with a definition, all right? And so here's our definition upon which everything we're going to do is going to depend. It says a function capital F is called the antiderivative of f of x on, I know I'm writing fast, I'm going to stop, don't worry, you can catch up, on some interval I if the derivative of capital F equals f of x for all x in pi. All right, now I'm going to just back away and let you write that down. I don't know why I walked across the room because you can't see me. All right. So what does this say? It says literally what you and I just wrote. All right. It says the functions, I kind of let the cat out of the bag there. The functions whose derivative turn out to be cosine, right? If their derivative turns out to be cosine, if f, their derivative, it's okay. I know it's going backwards. I've been here before many times with thousands of students. I get it. It's going backwards. It's okay. Your brain's going to switch. I know it. You don't. You think it's not. I know it will. Okay. We all learn to drive going forwards, and we eventually learn to drive going backwards. It took us a little bit of time. Some of us still aren't very good at it, but we all get the idea. This is going to flip for you. Don't panic. The antiderivative is the function that goes in here. And I already let the cat out of the bag. I told you there's more than one. And I know right now you're thinking, well, the answer to this is sine. And you're correct. It is. It is. Sine works. But sine's not the only answer. And if you're racking your brain trying to figure out whose derivative is going to be cosine, if it's not sine, I didn't say you were wrong. It's definitely going to be sine. But what about sine x plus 2? What's the derivative of sine x plus 2? Well, the derivative of sine x plus 2 is cosine. Because the derivative of sine is cosine and the derivative of 2 is 0. And if the derivative of sine x plus 2 is cosine, then you're correct. The derivative of sine x plus 21 is cosine. And the derivative of sine x plus 121 is cosine. And now we get to the fun of antiderivatives. And I'm sorry that I'm having a good time and you're not. But I didn't lie to you. I love this part of calculus. This is the part that I find the most fascinating. The antiderivative of cosine is sine. Plus 1, sine plus 2, sine plus 3, sine plus a half, sine plus pi, sine minus 8, sine minus 26, sine minus 247. The answer to this question is not one function big. How do we write this? We write it like this. We say the answer is sine x plus c, where c is a constant. That's how we write the answer. We tell the reader, you know what, if you take the derivative of a function like this, you're going to get cosine. So this is sine x plus c. We call this has a name, it's called the constant of integration. And what does that tell the reader? That tells the reader there are a lot of answers to this problem. It's not a one answer question. It's not. It's an infinite answered question. There's an infinite number of answers. An infinite number of answers. And like I said on the video, you don't want to forget this. Right? You don't want to forget this. If you leave this out. Okay, I am so sorry. How did this whiteboard move? Somebody tell me. When I erased, did it move again? Did I not move this whiteboard just a few minutes ago? Am I losing my mind here?
No.
Greg, wasn't this blue line at the bottom of the whiteboard a few minutes ago?
Maybe it's your camera who going
My
like
camera can't be moved. It's mounted on the light.
Yeah, because
All right.
yeah, you are correct.
All right. I'm sorry. I'm sorry to interrupt. But I'm sorry. It's driving me nuts. Okay. All right. Well, that's kind
I
of bad.
think when you lean on it, it moves up.
It can't move. It's on a 10-foot long pool table. Trust me, the thing weighs 3,000 pounds. I watched him install it. It's solid slate. So
But you can always go back to the video once you're done recording and then watch it.
Sam, you're acting like I really care.
Oh, okay.
Okay, I appreciate it, Sam. I sounded serious, but I was just killing time, Sam. Because, and here's why, Sam. Here's why I'm killing time. I've got no idea what to say after this. I don't understand this at all. I was lying. I don't know any of this. This is all further, Sam. I remember the book. So from here on, Sam, it's just all BS. So here we go.
Just help you.
All right. All right. So here we'll get back into this now. I'm ready. I'm back in. I didn't tell you a joke or anything to kill time there, and I'm sorry about that, but we're back in. So here we go. Who are we listening to? All right. Now that we're done with that. So what do we say about the answer to an antiderivative problem? Because the answer to an antiderivative problem looks like this, we say this is a family of solutions. We call it a family of solutions. That's what we refer to the solution to an antiderivative problem as. We say our answer to this question isn't sine x plus 1 or sine x plus 2 or sine x plus 3 or sine x plus 121. It's sine x plus any number you can think of, positive or negative, it doesn't matter. So there is an infinite number of solutions, and we call them a family of solutions in differential equations or in calculus. That's what we refer to them as, okay? A family of solutions. And we represent that family by putting sine x plus c, and everybody understands that when we write a c, we mean a constant. You pick the one you love the most, or all of them, it doesn't matter, they're all there. Now, what does that mean? Well, it means if you draw the graph of this, I think we all know that's the graph of sine. Now, that's not the whole graph of sine, it's just, that's the graph of sine x plus 0. Because we haven't shifted it up or shifted it down, we've just drawn sine x plus 0. But if we draw the graph of sine x plus 1, sine x plus 1 is also one of our answers. So while sine x plus 0 was one of our answers, sine x plus 1 is one of our answers. So when we try to draw the answer to one of these antiderivative problems, sine x plus 1 starts here, right? It starts here and it ends here and it goes like this. It goes up and it goes down and it comes back like this. That's sine x plus 1. But we don't just get sine x plus 1. We might get sine x plus negative 1 as well. Not might, we definitely do. So one of our answers is down here. And well, it's not down there, it's down here and it goes like this. And this is what we mean when we say the answer to an antiderivative problem is a family of solutions. Now, I only did sine x plus 1, sine x minus 1. Of course, there's sine x plus a half. That lives right here. And you get the picture here. We're going to be able to do sine x plus a fourth, and that one lives right here. And sine x plus 3/4, and that one lives right here. And in reality, all of them are on our graph. If we were to draw all the sine x pluses and sine x minuses, then our graph would just be a block of black. Because we can move it up whatever number we want and move it down whatever number we want. So that's what we mean when we say antiderivative problems have a family of solutions. Now, finding that solution is not any harder than it was when we wrote down those first three answers. If someone was to come back to us now, right? If someone was to come back to us now, let's get this out of here. Sorry, I thought I could erase it neatly, but it doesn't want to erase neatly. if someone were to come back to us now and ask us this question again, whose derivative equals e to the x, we now have a better understanding of the answer. We know what we wrote before was not wrong. We know, hey, if you take the derivative of e to the x, you get e to the x, but that's not the whole solution now. The answer is not hard to find. It's just as easy as it was before. We just remember to tack on our constant, remembering, of course, the derivative of e to the x is e to the x. The derivative of the constant, 0. Ta-da, we're done. So finding antiderivatives is never going to be complicated. It's not going to be one of those things that's going to overpower us. Now, there is the case, though, right? There is the case that we haven't talked about. And it's kind of weird that we haven't talked about this case yet, because it's normally the case we start with. And that is, whose derivative turns out to be x squared. You know, normally we start with the polynomials, don't we? That's our normal beginning point. We begin with the polynomials. That's where we begin. Now, to be honest with you, we're closing with the polynomials tonight. I know it's 7:30 and we're getting close to the end. Don't panic. We're closing with the polynomials tonight. Why are we closing? Not because they're hard, but because they take another layer of thinking. Whose derivative is sine? Probably cosine's involved in that, mister. That's my BHM spot. But how do we do this? Who do we take a derivative of to get x squared? Well, when we start, right? When we start, what's the power going to be up here to make it 2 after I take the derivative, right? I want it to be 2 after I take the derivative. So what does it have? It has to begin at 3. Because why? Well, because when you take the derivative of this, right? When you take the derivative of this, you bring down the 3. And then you take away 1. Now that's wrong. Not the derivative. The derivative is perfect. Everything written down here is perfect. The problem is we didn't end up with x squared. We ended up with what? 3x squared. Well, then how are we going to fix that? If I started with just x cubed, I ended up with 3x squared, but I don't want a 3 out in front. Well, okay, it's not rocket science. Why don't we just start with the x cubed and we'll put a 3 on the bottom. Now let's see what happens. Now we put a 3 on the bottom. Now there's a 3 on the bottom. Well, now 3 cancels 3 and we get x squared. Now you're right, I left a lot of room here, and you're correct, I left a lot of room so I can put the plus c in there. So let's take a look at the polynomial, right? The polynomial is the interesting case. Because let's ask ourselves, what exactly is going on? If I want to find the antiderivative of x to the 5th, what am I asking myself? I'm asking myself, who did I take the derivative of to get x to the 5th? Who did I take the derivative of to get x to the 5th? And we know when we take a derivative, we subtract 1 from up here. So we must have started with x to the 6th. Because when we take away 1, we're going to get x to the 5th. But if we take the derivative of x to the 6th, that's not going to give us what we want. We're going to get a 6 out in front and x to the 5th up there, and we've got that extra 6. So who did I take the derivative of to get x to the 5th? I took the derivative of 1/6 x to the 6th. And that's the answer. That's the answer. If you want to find the antiderivative of this, what do? You undo. Not to bring back algebra 2 nightmares here, but it sounds a lot like an inverse function. You undo what you used to do. When you used to take the derivative, you subtracted 1. So you do the opposite of that. It's called the antiderivative. You do the opposite of that. So what would you do? You would, when you took a derivative, what did we always say? We said subtract 1 from the exponent. So now instead, we're going to add 1 to the exponent. We said when you took the derivative, you put this person out here and you multiplied. Well, the opposite of multiplication is division. So we're going to add 1, going in the opposite direction. We're going to add 1, and instead of multiplying, we're going to divide. So if somebody says, what's the antiderivative of, and they give us a number, if they give us something like,
Hey, Kevin,
yes, sir.
that one that you just erased, the 1/6 x to the 6th,
Mm-hmm.
for an answer for that, do you write the plus c?
Yeah, yes. You would write the plus c with that. Yes, Adam, you would. So what is a homework problem going to look like for us? A homework problem for us is going to look like this. This is what, and I do a bunch of these on the video. A homework problem is going to look like this. They're going to write it as capital F, and they want us to go find little f. Little f is the antiderivative. They want us to find that. So they're going to write this, and they're going to write something like this. Like they'll write like x to the 4th minus 2x squared plus secant squared x. And they're asking us to tell them, who did we take the derivative of to get that? Okay, who did we take the derivative of? What did we take the derivative of to get this? And so the good news is when you write your answer, you can always check, right? You can always check by taking the derivative of your answer and seeing if you get back to the purple one. Now, what do? Well, we have a power. And our rule for powers is we add 1 and we divide by the new power. It's no more complicated than that. That is as simple as it is ever going to be. It's never going to be harder than that. Okay. What do we do here? Well, there's a 2 in front, so we just stick it out in front. Okay. Stick it out in front. We have a power, so we add 1. We divide by the new power. Now, secant squared, that's not a polynomial, that's not a power. We can't add 1, divide by 3. We can't do that. We ask ourselves, whose derivative is secant squared? And we all know the answer to that. We all know that if you take the derivative of tangent, you get secant squared. Now, we have to tack on our c at the end. And if we wanted to, which we do, if we wanted to check, right? We'll pick this cheerful green to check. If we want to check, what are we going to do? We're going to take the derivative of this. That's going to be 5 x to the 4th, and it has a 5 on the bottom. Because down comes the 5, we subtract 1. Now we have a minus 2, that's still out here. Down comes the 3. We're going to have x squared divided by 3. We take the derivative of tangent, that's secant squared. And we take the derivative of a constant, and that's 0. And if we simplify this, we get back to x to the 4th minus 2x squared plus secant squared x. And that's how we find antiderivatives. Okay, the answer to our problem is the red. Remember, the red is the answer. The green is our check. We just go backwards. We go backwards. Now, in your book on page 318, there's a table. Okay, there's a table on page 318. Now, I get the fact that all your tests are going to be open notes, open book. So you could just have this table on your desk while you're taking your exam. I'm fully confident in that. And I would probably even suggest it. However, if you don't have that table memorized, you'll never pass Calc 2. You just won't, okay? You would never pass my Calc 1 class on our second midterm and on our final exam without having that table memorized, because you wouldn't have had open book, open notes. So what is so significant about this table? Well, it tells us who all the antiderivatives are for the quote unquote easy functions, okay? That's what it does. It tells us that. And I think you're right, Sam. I think every time I lean on it, it moves. You're a genius. So let's just write down a couple of things that are in that table, all right? And nothing in this table is going to surprise you. There's nothing there's nothing about antiderivatives that surprises you. Now, you're going to need to watch the video on section 4.8, and I think I have a solutions video on 4.8, or I didn't make a solutions video, but I did a billion examples on the video, because I haven't had time, and nor am I going to have time to get through all of the examples. But what's in this table that's significant to us? Well, here's what they tell us. They tell us, and the way the table is set up, let's put my book right up here so I can see it, is it says, here's your function. Here's the antiderivative. Okay. And so what does it say? Well, it says, you know, your antiderivative of e to the x is e to the x. And in the book on the table, he says, I'm not going to write the antiderivative. I'm going to write this thing in math we call the particular antiderivative. Now, all that means is omit c. Now, why does he write it that way? So he doesn't have to spend the ink and the money to put a bunch of c's down in the table. That's all, okay? So e to the x, the antiderivative is e to the x. Whose derivative is cosine? We all know the answer to that. Sine. Whose derivative is secant squared? We all know the answer to that. Tangent. Then he says, whose derivative is sine? Okay. Now this one requires a little bit of thinking, right? Whose derivative is sine? If you want to say cosine, that's a good initial guess. But what's the derivative of cosine? The derivative of cosine is not sine, it's negative sine. Well, we don't want it to be negative. We want it to be positive. So I'm going to stick a minus on it. And now, when I take its derivative, I get negative sine times negative positive sine. So just like before, the ones that start with a C get a minus. Okay, just like before. Now, if you're going down the table, he says, whose derivative is 1 over x? Well, we know the answer to that. We know who you take the derivative of to get 1 over x. That's the natural log of the absolute value of x. We learned that derivative. So he puts on here the functions he thinks we're supposed to be able to remember off the top of our head. Whose derivative is x to the n? Well, that's x to the n plus 1 divided by n plus 1. Now, I added that one. It's in the table. He doesn't start with that one because what? Well, because for some of us, it takes us a little bit of time to remember that one. But we just have to undo what we used to do. We used to subtract 1 from the exponent and multiply, right? In fact, if you really want to talk about it, the order of operations was multiply by the exponent and then subtract 1. Now we add 1 and then divide. We have really flipped the order here. Now you'll notice in your book, you'll notice that he puts this in here, right? He says n cannot be negative 1. Because look right here, n is negative 1. Look what happens. We get undefined. So you can't have a power of negative 1. Why can't you have a power of negative 1? Well, the power of negative 1 is right there. That case is already handled right up here, 1 over x. That's x to the negative 1. Now there's a couple more that he throws in here, right? He throws in secant tangent. Whose derivative is secant tangent? We know the derivative of secant is secant tangent. He also throws in a couple that we may have forgotten. Whose derivative is 1 over 1 plus x squared? I mean, we may have forgotten that one. That turns out to be inverse tangent, right? That we were not real big fans of these derivatives when we learned them. And then he throws in whose derivative is 1 over the square root of 1 minus x squared. Now that we've seen inverse tangent, maybe we're going to remember that that's inverse sine. So he puts these in there, right? And he says also, if you have a constant times your function, don't worry about it. You're just going to keep the constant like I did in our example on your antiderivative. You're just going to keep your constant. And if you have a function plus another function, don't worry about it. You just take the antiderivative of the first one and you tack on the antiderivative of the second one. I'm about to give you the best news you've had all night. And it's not the fact that this works for negative as well. Here's the best news you've had all night. There is no product or quotient rule.
Yes.
I know, trust me. This is when I decided to major in differential equations. There's no undoing a product or a quotient rule. We will learn in Calc 2, and I say we because you're going to cheat on me with somebody else, but I'm going to feel like I'm there. You're going to go to Calc 2, and you're going to learn there is no product or quotient rule. There is none. This is what I meant when I said integration, anti-differentiation. Those are synonyms, guys. It's elegant, right? It's beautiful. It involves thinking, planning, and coordination. When you ask yourselves, who do I take the derivative of to get e to the x? That's not that elegant. But down here, things start to get more involved. So we'll close it out here. You need to go watch, not right now necessarily, but before you do the homework, I have some solid examples of other problems that I have not had time to work on tonight. And you need to watch those before you can be successful on this homework assignment. The homework assignment is 1 to 35 odd. It's rare on this piece of paper, right? I mean, there it is. There's that piece of paper. It is rare on that piece of paper that I gave you this semester for Cal State Bakersfield to have given you a homework assignment that looks like a high school Algebra 2 assignment, 1 to 47 odd, 1 to 35 odd. But we know in Algebra 2 in high school and in pre-calc in high school, that's what all of our homework assignments look like. Well, they have not done that, but they have done it in this section. Okay, in this section, they have done that because what? Because this section is really, really important. For us to be successful in chapter 5, we have to be successful in 4.8. All right, so I'll just come over here, put myself back on this thing. So oh no. Hey, by the way, it's raining at my house again. I don't know what it's doing at yours. So we'll close out for tonight. I'm probably going, like I told you before, I'm going to do 2 videos tomorrow, the best of my ability, try to get both those done. The other half of 5.2 and questions from 5.2, not yours, but mine. And then I will, if not, I'll have those posted on Wednesday. So Wednesday night, we talked about 5.1. It would not hurt for you to read the book or watch the video or both, he says optimistically, before I see you on Wednesday night. All right. Everybody have a great evening and safe tomorrow so far. Everyone's here each day, so that feels good. And I will see you Wednesday evening. All right.
Everybody want us to put our recommendation?
Yeah. If you want to put them on reminder, put them on email. I'll deal with it either way. And then I will send you a remind tomorrow telling you when we're going to have the quiz. All right. Remember what it covers. And if you didn't see what it covers, it's at the beginning of this recorded video, which will be up as soon as everything converts and I can get it posted to my YouTube channel. All right, everybody?
Thanks,
All right,
Kevin.
guys. I miss you. I really
Thanks,
do. It sucks. I mean, I know you're not having fun either, but trust me, nor am I. All right. I miss being in class. I can't tell you how much I didn't I never intended when I retired from high school to stop teaching at Cal State. We were always going to teach at night at Cal State just for the extra money. And now both of us are like, oh my God, I can't live without teaching. So we're going to be out there forever. All right, guys. So we will see you soon. I'll see you on Wednesday night. All right.
Alrighty.
Good night, everybody.
All right. Good night.
Right.
Bye, everybody.